Welcome. This is one of my absolute favorite topics, and I'm happy to be here to share it with you, everything that's wrong with IT. And you know, IT is like the weather. Everybody's complaining about it, but nobody's doing anything about it. But now, you're gonna help me, okay? My name is Sten Vesterli. I'm an independent consultant from Denmark. Now, the purpose of a consultant is to come in and help the client. The purpose of a consultant is not to come in and bill as many hours as possible. Now, the typical consultant model is that the longer it takes for the consultant to solve your problem, the better for the consultant, which I'm not a big fan of, which is why I only work on a fixed price and based on the value that I'm providing to the organization. And the value is the part that is central. Value of IT is central to what we're doing wrong. You see, we are the most laughed at profession. This is Google Trends, and as you can see, IT jokes clearly beat out every other profession, lawyers' jokes, doctor jokes, engineer jokes, etc. As a matter of fact, there are 414 million hits on Google on IT jokes. Now, since there's only 25 million of us, that means each of us get about 16 jokes. Now, that's because we're doing something wrong. What we're doing wrong is what we built, how we build it, how we roll it out, and how we maintain it. So, if only we can fix these 4 things, then we're good. So let's see. We'll start. I'll need a volunteer. Have a look at this watch and tell me. I'll come back to you in a few minutes and tell me what's special about it. Have a look at this one. See what's special about that one. Have a look at this one. See what's special about it. Okay, so I'll start out with one of my favorite technology examples. You know, a common problem is sock sorting. So when your socks come out of the dryer, you need to sort them into pairs. And of course, technology can help us do that. So there are various options, and the one I have is, you see, this is not just any sock. This is a smart sock. And what makes it smart is this little button. You see, this is not just a button. This is an RFID chip. So my smart sock has an RFID chip, and I have this device. This is my sock sorting device. So what happens when my socks come out of the dryer? I'll pick up a sock. I'll get out my sock sorting device, and I will start my sock sorting app. Then what happens is I will scan the chip on my sock sorting device. It will communicate via Bluetooth to my sock sorting app, which will then communicate via Wi-Fi to the international sock database in Zurich, where it's stored, all the information about my socks are stored. So let's see how it works. So I will take my sock and I will scan it. Oh, so this sock has been washed 7 times. It has ID number 045ACB, etc., and it's a right sock. Good, I have 1 sock. I'll get the next sock out of the dryer. I'll scan it. Oh, didn't match. I'll have to put it back. I'll take the next sock out of the dryer. I'll scan it. Oh, it didn't match. Now, those of you who are into databases will notice, I'm doing a full table scan here. I'll take the next sock out. I'll scan it. Oh, there they were. It's a match. So I can save that now these socks, they're matched. And, and the international sock database is updated that they've been washed 8 times. Now, how many believe that this is something I just made up? Hands up. How many believe this is a real product? Hands up. The second group is correct. You can go to blacksocks.com, and for only 159 euros, you can get 10 of your own internet-connected socks and a sock sorting device. Now, whether this is, an appropriate use of technology, well, that might be questionable. The point here is that sometimes we're building something And it's getting so complicated that we lose sight of what we're actually trying to achieve. So I'll show you another sock sorting device. This one. So you see, the way this one works is when I take off my socks, I will put one sock, two socks, and they will go together through the washer, through the dryer, they'll come out, and I will have saved, RFID chips. I don't have to charge my sock sorting device. I don't have to let the international sock database in Zurich know how many times I've washed my socks. So the next time you're building something that might look overly complicated, then think about the sock sorter anti-pattern. Okay? This is something to avoid. Another of my favorite devices, this one, a little flashlight. And it's from the friendly people at Oracle, some speaker gift from some time. And I keep it on the table next to my bed. So just in case the power goes out. Now I don't live in California, so we do usually have power, but just in case. So when you wake up in the middle of the night and you try to turn on the light and oh damn, the light's out. Then what's the next thing you think? I need a beer. Now, fortunately, the friendly people in the Oracle Gadget department, they have anticipated this need. So this flashlight that I'll turn on is also a bottle opener. So thanks to Oracle, I will never be thirsty in the dark again. Now, what this is telling us is these are two completely unrelated features that have been bundled into the same product. And what happens is, with these unrelated features is, you see again and again, well, now we have the database, and we have set up the application server, and we have the deployment infrastructure, so we need to have this little extra feature. And it's just easier if you just sort of squeeze it into the monolith. And the monolith gets bigger and bigger and bigger, and nobody ever thinks of actually building a separate service because of the overhead. So if next time you're tempted to just squeeze an extra feature into your monolith, then think about the flashlight bottle opener anti-pattern. So let's see the watches here. So this one, what's special about it? Yeah. You can't get what the time is. Well, it has only one hand. It only has the hour hand, because this is the watch I wear when I'm out on the town. I don't need to know how many minutes exactly there is. I just need to see, oh, well, it's getting about 3 a.m. Maybe it's time to go home. So this is just a variation of a watch. This one, anything special about it?
It has some arrow that I don't understand from 0.
Yes, it has a 0 to 100, an extra arrow. This is actually an activity tracker, and unique among activity trackers, it looks like a watch. And it tracks my step and my sleep, etc. So, how about that one? It has times in 2 time zones. Yes, well, it has 2 times, but it's actually has the time and it has a countdown. You see, I've set this to when I retire. So you see, until my retirement, I have 21 years, 6 months, 17 days, 6 hours, 6 minutes, and 14 seconds. So whatever I need to do with my life professionally, that's the time I have left. What these devices show us is that if you have a physical constraint like electromechanical engineers, people who build watches, then they have constraints. They have to limit themselves to specific features. These specialized devices, there's one watch that does this, there's one watch that does that, but they don't do everything. And that is a good idea for building IT, not shoveling everything into the same product. So, this is an elevator in Mumbai. So I was giving a presentation there at a big conference, and I was up on some high floor and taking the elevator down to the ground floor where the conference was. Now, how many have been in an elevator? Yes, we know how elevators work. or we know how they're supposed to work. Only this one didn't. You see, when I got into the elevator, I pressed the ground floor button, and the elevator would start moving. And sometimes it would take me down to the ground floor. Sometimes it would stop halfway. Somebody else would get in and look at each other, and the doors would close, and the elevator wouldn't move. I'd look at the other guy would look at me. And then at some point, the elevator started moving. Often down to the ground floor. Sometimes it started moving back up again. There's something weird here. I have to figure out what it is. So I started investigating and taking notes on the elevator. And you see, what happened was that when I was alone in the elevator, I go in, I press the button, it takes me down to the ground floor. It works. So obviously, it's not a problem with me. It's obviously a problem with other people. So when other people come into the elevator, they mess things up. So I investigated it further, and I finally discovered that the friendly people at the India Elevator Company Limited had invented a feature. They have added a feature to this elevator that no other elevator has. And if you remember Kai Horstman's presentation about features that were added to Java that nobody was asking for, okay, this elevator had a feature added that nobody was asking for. The feature that you might change your mind. So when you go into an elevator, you press the ground floor button. You have indicated to the elevator, take me down to the ground floor. Now, but some clever, smart-ass programmer thought, well, what if he changes his mind? Well, if the second time you press the ground floor, you cancel it. So the second person to come in would cancel the order, which meant the elevator would just be hanging there in midair with two people in and had nowhere to go, had no instructions. So eventually somebody would fortunately call the elevator, because otherwise we would have starved. It would go up or down. Now, there's something called user experience patterns. If you work with user experience professionals, they will tell you that we build mental models of how things are supposed to work. We know how elevators are supposed to work. If somebody builds an elevator that does not work the way we expect it to, then strange things happen. We need to respect these user experience patterns, and we need to build our systems like people expect them to work. Anybody know which movie this is? Gravity. Yes, and so Sandra Bullock is up in space, and there's a big disaster, and George Clooney gets killed, and she's all alone, and her space shuttle is destroyed. But fortunately, there is this Chinese spacecraft that's just sort of drifting there, and she just manages to get into it, and she's sitting in front of the panel in this sleeping spacecraft, and everything is labeled in Chinese. And she's looking at it, and then she reasons, well, this looks like a Soyuz craft, the Russian one that she was trained on. And on Soyuz, power is upper right. And she presses the button, and of course, the spacecraft comes to life, and she manages, of course, to save herself and land on Earth, and everybody's happy. That is a user experience pattern that power is upper right. Now, we might not need to operate unknown spacecraft, but we do need to build systems that conform to the way our users expect them to work. Then there is, how we build it. So how we build stuff is, I'll go up, the manager says, I'll go upstairs and find out what they want, and in the meantime, you guys start coding. So that's how we're building systems, and not terribly good. I have a lot of good examples from the public sector in Denmark, where we are building IT disasters, and one of them was a program to collect money that was owed to the state. Now, the way this works is if you don't have an ongoing budget for improving your system. You have a big project. At some point, it is decided that we're going to spend a number of millions on this specific project. So what happens is it gets specified as the everything project. So, you know, it's supposed to do everything, so and be so flexible and so configurable that I'll never need to talk to another programmer again. So we build in parameters to make sure that you can reconfigure it. And I've built lots of these parameterized business logic applications, and nobody ever changes the parameters. But the problem is we're spending all of this time building the everything program, the program that will solve every problem, every conceivable problem. In this case, they were building this claim program to collect money from citizens of Denmark. And they thought, well, we have to make it flexible. So it has to be able to handle, you know, various types of claims, and there are various rules. So they thought, well, maybe we have 8 or 10 different claim types, but we need to have it flexible. So they specified a very flexible system. And the programmers were supposed to build something ultra flexible that could handle any kind of collection under any kind of circumstances. So when they designed the system, they thought, well, maybe we have 8 or 10 different types of claims. That, you know, there could be parking tickets, there could be back taxes, there could be child support, whatever it was. And there were a few rules, like if you had, they were not allowed to take more than X% of your money. The claim would be too old after a specific time. So there might be a few dozen rules. And then the programmers delivered the system, and by the time they had gone through all the rules and regulations, they figured out that there were actually not 8 or 10 different claim types. There were 400. There weren't just a few dozen rules. There were 700 rules. So the everything program, of course, worked brilliantly. You could just pass it off to the business and say, as soon as you have made these 280,000 decisions, the system works. Now that's the everything program anti-pattern. Don't build this kind of ultra flexibility into your system. Push back against the business if they want that. Because what happens is the time we spend on programming a system that will do everything forever is better spent building a system that actually provides value now and changing it a little bit later. Of course, we have the problem with these systems that if your budget procedure is that you get one big budget for a project, you're going to shove everything into the project. So you need to, we in the business need to push back against this project-driven approach where now we have a huge pile of money, we'll build a system, and then we have zero money to maintain it forever after. This is a chicken gun, and you can see the chicken out here. This is from, you can probably see, this is the guy from Mythbusters, so this is where it's from. It's not from the original chicken gun. So what do you use a chicken gun for? Well, of course, to shoot chickens. What do you shoot chickens at? You shoot chickens at aircraft because you want to simulate what happens. It's a test. You want to simulate what happens if a bird hits the aircraft. The original chicken gun was invented by a guy who had invented plexiglass. Plastic type of plastic glass. And you know, the aircraft industry is pretty conservative. The front shield of an aircraft had always been glass, thick glass. We knew exactly how that worked. And he claimed that a plexiglass would be solid enough. The industry was skeptical, so he decided to set up a demonstration. So he invented the first chicken gun. And so he had the chicken gun, and he had this plexiglass shield, and he was sitting on a chair behind it because he was so certain that his plexiglass shield would take the impact from this bird. And he gave the signal to his assistant. The assistant fired the chicken gun. The chicken came barreling out of the gun, through the plexiglass, sending shards all over the place, just narrowly missing the inventor and slamming into the wall behind him. So what happened? Well, the problem was that this test was performed with a frozen chicken. So if you had a non-frozen chicken, it would have been the correct test. It would have made a mess against the plexiglass shield, but it wouldn't have gone through. But effectively, he was shooting a 5-pound hailstone at his plexiglass shield. Fortunately, the gun wasn't aimed all that exactly, so he escaped with his life. Now, this is a manual test. A manual test will go wrong. Sooner or later, somebody's going to do it wrong. So the next time people say, well, you know, it's easier. We can just do a manual test. We don't have to automate this. Now, manual tests, that is the chicken gun anti-pattern. Like, you can refer to that when people say you can just do manual tests. This is a Chinese high-speed train. The Chinese built a lot of high-speed trains over a very short period, and they had to build them on these elevated carriageways because, well, they needed to be pretty straight, and you couldn't, and there were all kinds of obstacles, so you couldn't just put them straight through the cities. And they built a lot of them in a very short time, and they were carefully specified because, you know, in China they have earthquakes, so an elevated carriageway like this, and you want it to be pretty solid. So they had calculated how to build these. And they built a stretch of these, and there was an earthquake. Not a very strong one, a little earthquake. And a section of it fell over. Oops. That shouldn't have happened. So they went out and investigated. It turned out that the contractor building that section had been sort of pressed for time. And it takes time for concrete to set, especially if it's a large area. So what they did was they put bamboo scaffolding in the middle of the pillar and only had concrete around it, which meant that from the outside, it looked pretty good. It just, as soon as an earthquake came along and shook it, the whole thing fell over. You see, that is one of our problems in IT. We have the project triangle. If you were to, at James Burney's presentation, he talked about, you know, the iron triangle. You have cost, scope, and time. So for a given quality, if you fix 2 of them, the last one gives itself. If you know what the scope is, if you know how much time you have, the cost gives itself, etc. The problem in IT, now that has worked well. Project management always talk about this one. But they didn't account for IT because we don't have a triangle, we have a square. What we have still have cost, scope, and time, but we have quality. Quality is not invariant in our case. Now, if you're building a physical thing like a watch, then you can recognize, anybody can recognize the quality. When you build something like IT, what happens is when you fix these 3, then the 4th one moves, and quality just degrades. But we can't tell, or maybe only those of us who built it can tell. So that means it's not enough in the test of a system, or especially in the test of a component that comes in from somewhere else, that you go, you know, and knock on it, yeah, it sounds like concrete. Because then you'll end up with the bamboo scaffolding anti-pattern. Like there are hidden defects, and unless you actually take the damn thing and shake it, you're not going to get the data you need. You're not going to get a realistic test. So if all builders build buildings the way programmers write programs, the first woodpecker to come along would destroy civilization. That was an IT joke, so we've only got 413 million and a few 100,000 to go. Now, I'm a pilot, so I fly little Cessnas and Piper aircraft for fun, and pilots are obsessed with accident reports. You see, what happens in flying is that accident is actually investigated to figure out what was the cause and to make sure that it didn't happen again. And this is not a funny story. This is data from the flight recorder of a 737 MAX 8, the one that crashed in Indonesia, the Lion Air flight. And it had this computer system that was supposed to help the pilot keep control of the plane, the maneuvering characteristic augmentation system. The problem with this aircraft was it was supposed to fly just like the old models. But they had to change, they needed a bigger engine because it was more fuel efficient. In an aircraft, there has to be a careful balance between the center of lift and the center of gravity. So lift and gravity and center of gravity. If the center of gravity is forward, planes will tend to nose down. If the center of gravity is behind, the plane will tend to nose up. You correct for that with a trim. Out of the tail, there's a little trim that you set so the plane flies straight. The problem with the 737 MAX 8 was that these big engines that were placed in a different position, they would tend to, in certain situations, if you had the nose too high, then the air hitting these big engines would actually generate extra lift, which would lift the aircraft further up, generating more lift, until the aircraft was in such a steep angle that the wings stopped generating lift, and the aircraft would fall out of the sky. Fortunately, Boeing had a solution for that because they'd already encountered that problem in the 737 military tanker, 737. So it had big tanks under the wings. Same thing. If the aircraft nosed up too much, it would get out of control. So they already had software that would gently push the nose down. Problem was that when they implemented this software in the civilian 737, they figured out that there was actually also a problem at low speeds. So the original software was connected to both of the angle of attack indicators. There's a little arrow, like a weather vane on both sides of the plane that shows how high the nose is. That's these two lines here, the red and the green. In the military aircraft, both of those went into the computer system, and it also had an indicator for the G-force, how much power if the aircraft was maneuvering heavily. So it was a nice piece of software. It worked well in the tanker. They put it into the civilian aircraft, but because they had to use it at lower speeds, they had to make a few changes. At lower speeds, there wasn't the G-force. So, you commented out that part about the G-force. And then, by the way, the civilian aircraft wasn't connected to both sensors, it was connected to one of them. And, by the way, because it now had to work at slower speeds, the trim, it had to maneuver the trim more, so it got more trim authority, it could move the trim more. Which meant that a piece of software that was completely valid in one situation was put into another aircraft. When the computer got the wrong information, the wrong angle of attack, it started pushing the nose down. Now this here is normal. There's some normal operation here during takeoff, and then at some point, it suddenly pushes the nose down, and the pilot manually trims it back, and the computer trims it down again, and the pilot trims it back. And this is the computer, and this is the pilot, and the computer and the pilot are fighting over control of the aircraft for 8 minutes until the computer wins, maxes out the trim, the aircraft crashes. So what happens here is you take a piece of software that is completely valid in one situation and you move it into another environment without proper care. This was what happened here. It shouldn't have happened. It shouldn't happen in any software, and especially not in mission-critical software like this. This is a cockpit of a 737 MAX 8, and the reason the pilots weren't told about this software was that there was an existing procedure. If they had a trim runaway, you would just flick these two little switches there and you would be safe. So down here, behind the power, there's the trim cutout. Problem was that this was tested separately. So if the plane was flying along nicely at 35,000 feet and suddenly nosed down, the pilot has 4 seconds to react. Now, if that's the only thing that happens, suddenly the aircraft suddenly noses down. He'll know what to do. He'll reach down. That's an instinctive reaction. He has been trained for that. But during takeoff, when the computer is being fed garbage data from the sensor, the cockpit is full of errors. It has the master caution. It has the stick shaker from the stall warning. It has various lights and alarms. And the pilot cannot possibly diagnose the problem and flick these 2 switches in 4 seconds. If he doesn't do it in 4 seconds, the forces on the trim, they're so strong that he can't even trim it manually. And he doesn't have a chance. What happens here is that this was also approved based on an unrealistic test. What happened was this was not a full, real test. They tested this component. These switches, they work if this one thing goes wrong. But if you actually have a million things going wrong or 12 warnings, you don't have the time. Which is why, this aircraft is going to be certified again, and we're getting smarter. The aircraft are going to be tested in more realistic scenarios now. This is a 40mm Bofors anti-aircraft gun. I commanded a platoon of these back in the 80s in the Danish Air Force. And I had 2 of these guns, and I had a fire control radar with a fire control computer in it. And to shoot down aircraft with cannons, it's kind of a complicated thing. So the radar is up here. It knows that in this direction, in this angle, at this distance, there's an aircraft that you're going to shoot down. It also has to know that there's a gun over here at this elevation, in this orientation, and it'll have to calculate, okay, the plane is coming like this. So I'll send an instruction down to the gun to turn out in this angle, this high, so the projectile will fly, and after 4 seconds or whatever, it will meet the aircraft. Kind of complicated. Now, this was a system built in 1963. So this was what it looked like. So it was based on vacuum tubes. It was actually quite sophisticated that you could do all this math with vacuum tubes, and you had spinning gyros and all kinds of sophisticated stuff inside this fire control computer. Now, this was built by electrical engineers. And electrical engineers working with vacuum tubes, they know there's a certain tolerance. Things are not exact. So when we had aligned everything carefully, we would do a test. So we would inflate a big, huge balloon, a big helium balloon, big red balloon, and you put a radar reflector under it, basically some aluminum foil, and then the gun commander would put a little mirror down where the projectile would go, and a little crosshair out at the end of the gun. So we would release this balloon, the radar would lock onto the balloon, and the gun commander would look through the mirror out through the barrel of the gun. I would flick a switch on my computer, so it took out the lead, aiming before, so it should be aiming straight at the balloon. Typically it wasn't. But it didn't matter because I had a cheat box. So I had a little box, so I'd be talking on the radio with the gun controller, and he would tell me up a bit, turn the cheat box, left a bit, yeah, now it is, now it's there. That worked, and we could get pretty close. When we had our live fire exercises, there's this sensor that comes flying in, and it measures how close you are, and we were close enough to be able to shoot down an aircraft. Now, then we got upgraded to modern digital computers. Now, electrical engineers, they knew that we would need a cheat box because reality is messy. Computer engineers apparently don't know that the world is messy. So the new system, the new upgraded system, didn't have a cheat box. Because, it was all digital and all very precise. So there was no need for the cheat box. And we couldn't hit a thing. And then I left the Air Force. Now, the point here is that real life is messy. And we can be lulled into this feeling that everything is exact. It is not. So what happened here was what I call the techno-arrogance anti-pattern. We believe that we can solve everything with technology, and we can solve it exactly, and we have everything we need. My old system had the cheat box, which it needed. So let's see, oh yes, how we roll it out. So, well, Radbert, the consultant from Dilbert, he says, well, we'll turn off the old system and we'll turn on the new system. And Dilbert reasonably says, well, what happens if the new system doesn't work? Won't it have devastating economic consequences? Let me check. No, I get paid exactly the same. Now that's what happens when we roll out IT systems, and IT does not have any responsibility or any share in the value of the IT systems. We have, we had a system, brief story, another public sector Danish system that didn't work. So we had the deed registry, who owns what land. That was all going to be digitized. Now the people writing in the old books there, they were public servants and they had very long notice times. So we were going to digitize it. But these people had to be paid for 2 years after they were given notice. So the new system is going to be rolled out August 1st, 2012. And we don't want, after that, we don't need all these old civil servants. So of course we'll fire all of them, or half of them that we don't need anymore. We'll fire them August 1st, 2010. Because then, after the 2 years, when the new system comes, we don't have to pay them salary. What could possibly go wrong in that scenario? Right, of course the system was delayed, and we didn't have the people, and they had a backlog of cases, and they couldn't figure out the new. Yeah, it was a disaster. We have lots of those. Here's a better story. So this is an aircraft story where nobody dies. This is from a simulator, of course, but it shows United Airways 1549 out of LaGuardia, the Miracle on the Hudson. Okay, so here it's flown through a series of, it's been hit by a flock of birds. No need for a chicken gun here. And you might have heard the communication with the controllers, because that's public, but the accident report contains a transcript of what they were actually saying in the cockpit. And what happens there is that you hear dunk, 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 the birds are hitting. Uh-oh, I got both rolling back. So the RPM on the engine, both engines are stopping. And the Captain Sollenberger, grabs the control and says, my aircraft. And the co-pilot releases his control and says, your aircraft. Now he's at 3,000 feet. An aircraft like that doesn't glide very long. So he's got 155 lines on the line. And what does he tell his co-pilot? He says, get out the QRH, loss of thrust, both engines. The QRH is the Quick Reference Handbook. So this is the list of procedures that you do in an emergency. So his co-pilot gets out the QRH and says, start reading through. If fuel remaining, engine mode selector, ignition. Ignition, the captain confirms. Confirm thrust levers idle. Idle, captain confirms. And they go through the checklist. Now, they have lives on the line. And they read the manual. Now, my bloody users won't read one page. Now, we used to send people who were going to be using our systems, we used to send them on training classes. They would have to learn how to use the system. Now, in 99% of all cases today, we don't have that luxury. So that means that we have to have systems that are not that complicated. I don't have, let's see, now I don't have the time to, this is a parking meter in New York City. It's a perfect example of how not to do usability. And I was sitting outside a restaurant waiting for a friend, and in 20 minutes I noticed 6 people trying to operate this. 2 of them succeeded. One of them tried coins, couldn't get it to work. One of them tried credit card, couldn't get it to work. One of them tried to download the app, there was a QR code on the side, couldn't get it to work. And one couple got into an argument in front of it because neither of them could get it to work. And they gave up, but they were still arguing as they were walking down the street. Now that's about a 33% success rate if your point is to maximize parking fees. Now, if your point is to maximize illegal parking fines, then this device is a smashing success. Okay, so we've got how we maintain it. This is an open disk system. My first job at a university, we had a mainframe from the 70s, and it had a disk drive like this, 200 megabyte disk drive. Amazing power. And so when you got in the morning, you would open this. So here the lid is off. You see the next one has the lid on. You'd open the lid. You would take the platters there. You would take off the dust cover, and then quickly, so no dust managed to settle on it. Quickly but carefully, you would place the disks, the stack of disks in the machine. You would close it, close the door, press the button. It would spin up like a washing machine, and then you would go to the typewriter terminal, and you would say, "Load," and it would work for a while. Then the typewriter would type, "Operating system loaded." Then you would spin it down, open the lid, take out the plates, quickly but carefully, put the dust cover on, take the dust cover off the application, put the application in, lock it, close it, spin it up, type a few commands on the typewriter, and then we were in business. The problem here was, of course, that we'd had this system for a long time. And we had a very nice contract with the supplier of this mainframe. So that was made 25 years ago, and I don't think he was making much money on it. But the wonderful thing about that contract, which was our problem, was that the vendor could not cancel it. There were no provisions for the vendor to cancel it. As long as we kept paying, then he had to keep supporting it. And the university had, of course, never saved any money for a replacement project. We didn't have the money to replace the system, so we would just keep on going, and every year, we would just still be using this system. At some point, of course, eventually something fails. And one thing about these big old mainframes is when they fail hard. So, if a disk drive fails in your device, like if it fails in your laptop, it just doesn't boot. If it fails in a desktop, maybe you have a little red light. When a disk controller fails on one of these, there are flames, there's smoke, there's fire alarms, it's a whole shebang. So we had everything shut down, and the engineer comes out from the mainframe vendor, and whenever somebody retires one of these, the vendor takes it and cannibalizes it, takes it apart for parts. And he comes in and he cleans out the soot out of this burned out machine, and he puts in this big circuit board that's the new disk controller. And he puts it in, and then he says, "I'll just have you know that this is the last RC7000 disk controller in the universe. So when that one goes, I can't help you. Have a nice day." And then I quit. Now, the lesson here is, of course, that we cannot what we do is we have this big, huge project bundle, and then we have no money for maintenance, which is why we're running all these old legacy systems. We could replace them, but if we in IT don't have a discussion with business about, a physical machine, you have depreciation. You know that it will be worn out of 10 years. But we say, but this is an IT system. It doesn't get worn out. Well, it does, and we need to tell the business. Let's see. Yes, let's end on a positive note. There's still just short of 1 billion people who don't have electricity, and of course there are technology solutions there. Here's an old one, 1990s solution. So it's a radio, and it also has a flashlight. And the way we generate power is with this little handle. Now the problem is, of course, that we didn't have LEDs. We just have a regular light here. So when we turn it on, didn't last long. Now, if I were to spin the handle for several minutes, I might get a few more seconds of power. But the technology wasn't really there to replace to get power to the people who needed it. Here is a more modern solution. So this one this is a gravity light. You might not have electricity, but you do have gravity. So what happens is you fill up this big bag with rocks or sand or whatever you have, and you raise it up, and then the power of gravity pulls down, and you have light. Now that is technology that really makes a difference. Now, it doesn't really, it did have some problems. The problem was, of course, that it doesn't run for very long and it only has this limited light. But technology is moving forward. I was just supporting this one on, this is the next version of it, on Indiegogo, doing a Kickstarter campaign there. And this one, the next version, now it has a battery. We didn't have a battery in that one. 2012 designed 2011, we didn't have very good batteries, or they were very expensive. You wanted something that you could actually go out and sell to people who didn't have very much money. You wanted to go out to the poorest of the poor and give them this solution. And this one, while it did work, it had some challenges. This one has a battery. Now we can create batteries at a lower cost. So it can be connected to a solar panel. And of course, this one didn't even have a USB, a phone charger. This one has. And then the final thing is, if you look at the use case, something that you only figure out when you try to sell it, this one, the gravity light, is a good deal. It makes sense. You save the money you save on kerosene for your lighting will quickly pay for this device. Only the problem is when you go out and actually take it out in the real world and actually try to present it to the people, to the users, the buyers, the people who should use it, you figure out that even though they could save money, they don't have the money to invest in it up front. So they could save money, it would make sense for them, but they don't have the $40 it cost them to buy one of these. So the people behind it went back to the drawing board, and they came up with this solution. This solution has micropayments. So you give it to somebody, and they will pay $2 for it, and then after 30 days, it stops working. But it has a code. So if you go somewhere and you pay $2 and you transfer it from your mobile phone, you get another 30 days. So this one, you can actually get it. The business model works. You can give it to people. They can pay as you go along. You would never figure that out. You wouldn't discover that unless you tried something first, like the gravity light. So this is technology that makes the world a better place. So, I told you what's wrong with IT. You remember 4 things wrong? What we build, how we build it, how we roll it out, how we maintain it. It boils down to the root cause here is that we in IT do not discuss value with the business. We just build whatever we're asked to build. We need to ask why. Why do we want to build it this way? Is there a better way to do it? And I would like you to help me. We're in this together. So I would like you to connect with me. You can go to the vesterli.le/link. That takes you to my LinkedIn profile. You can just search for me on LinkedIn and connect with me. And I'll send you my email and my Twitter handle, and you can sign up for my newsletter, all that stuff. If you're a CIO, I'll give you a free subscription to the Valuable CIO newsletter. And then, of course, you need to go back to your organizations. And you need to educate them. You need to tell them. You see, there are all these anti-patterns. So you see, this is the sock sorter anti-pattern. This is not the way we're supposed to build it. And you need to educate your organization. I'm hoping that you can do it now. I've tried to give you some arguments. You might need some external help, and you can, you go out and hire somebody like me or James Burney or somebody of the other people here who tell you about how to do IT right. Because, I want you to help me. We're in this together, and we need to make IT live up to its promise. Thank you.